When we're talking about right angle triangles, we're essentially talking about trigonometry that takes place in quadrant 1. It's time to expand that knowledge to the other 3 quadrants, to the entire coordinate plane. Let's start by finding the sine of each of the angles on the left-hand side. The sine of 30 degrees turns out to be 0.5. Plugging sine 150 degrees into your calculator also yields 0.5. The sine of 210 degrees, on the other hand, is negative 0.5. Same value, but with a negative sign. And the sine of 330 degrees, also negative 0.5. What do all of these angles have in common? Why are they giving us one of 2 answers, the positive or negative version of 0.5? Let's draw them on the coordinate plane. In quadrant 1, we have 30 degrees. 150 degrees, that's an angle in quadrant 2. It's 150 degrees. 210 degrees is in quadrant 3 and looks like this. That's 210 degrees, and 330 degrees is roughly over here. 330 degrees. What do they each have in common? Well, each of these angles is 30 degrees from the positive or the negative x-axis. In quadrant 1, it's clear that 30 degrees is 30 degrees up from the positive x-axis. 150 degrees, if I take another 30 degrees and add it to it, gives me 180. 150 degrees is 30 degrees up from the negative x-axis. 180 degrees plus 30 degrees, 210 degrees. So we're 30 degrees down from the x-axis to get to 210 degrees, and 330 degrees is also 30 degrees down from the positive x-axis. We call this 30-degree angle the reference angle. Let's explore that a little further. Let's start with this example. We're asked to solve for theta 1, a quadrant 1 angle, and theta 2, a quadrant 2 angle. All right, so we're told that the quadrant 1 angle, the terminal side rather, goes through the point 3, 4. So we have a 3, 4, 5 triangle where the x value is 3, the y value is 4, and we're told the r value is 5. This is, of course, a right angle triangle. Let's calculate the sine of that angle. The sine of theta 1, sine is y over r, is 4 over 5. That's enough information to calculate the value of theta 1. Taking the inverse sine of both sides gives me theta 1 is equal to the inverse sine of 4 over 5. And my calculator tells me that in degrees, this is 53.1 degrees. So we found the value of theta 1. What about theta 2? Well, we know that the x value is negative 3. This is, of course, a right angle triangle as well. The y value is 4, and once again, we're told that r has a value of 5. Note that while x and y can be either positive or negative, the value for r, the value for the hypotenuse, will always be positive. All right, so the sine of theta 2 is also y over r, so the sine of theta 2 is also 4 over 5. We know that when we take the inverse sine of 4 over 5, we get an angle of 53.1 degrees. But 53.1 degrees is in quadrant 1, not in quadrant 2, where clearly the terminal side of our angle resides. So what is the value of 53.1 telling us? Well, 53.1 is actually the reference angle. So rather than finding theta 2 directly, so far we found the value of theta ref, the reference angle. And that's right here. Because I can see that my angle is in quadrant 2, and even if I only had the coordinate that the terminal side passes through, I would realize that this angle is in quadrant 2. I need to recognize that my reference angle will help me to find the actual angle in this way. Theta 2 is 53.1 degrees short of 180 degrees. So we find it by taking 180 degrees and subtracting 53.1 degrees. What do we get? 126.9 degrees. So unless we know that our angle is definitely in quadrant 1, we assume that we're always finding the reference angle, and while it is possibly the answer to our problem, we may have to do an initial, or a second step rather, in order to find the final answer. Let's play with that idea of a reference angle a little bit more, just to make sure that we've got it. So 14 degrees is our reference angle. So we're essentially told that theta ref is equal to 14 degrees, and we're being asked to use that information to draw an angle in each quadrant. Well, in quadrant 1, we simply would have an angle of 14 degrees up from the x-axis. If our angle is actually a quadrant 2 angle, and this is a bit of an odd question because we're not told which quadrant the answer is in, we're just told to imagine it could be in any of the 4 quadrants. Well, if the reference angle is 14 degrees, then the quadrant 2 angle is 14 degrees up from the negative x-axis. That gives us an angle in standard position, so starting from the positive x-axis, of 180 degrees minus 14 degrees, or 166 degrees. If our reference angle is related to an angle in quadrant 3, the reference angle tells us we are 14 degrees beyond 180 degrees. And 180 degrees plus 14 degrees is 194 degrees. So in standard position, we would label this angle as 194 degrees. Incidentally, we could also label it by its coterminal angle, the negative angle. We could just as easily give it this name. So that would be 180 degrees minus 14 degrees, so 166 degrees, but of course it's in the negative direction. So the value would be negative 166 degrees. That's just an aside. In this question, it's most important that we just label the angles in one way, so why don't we label them using the positive version, the positive coterminal angle? All right, so for the last quadrant, if my reference angle is 14 degrees, then my actual angle is 14 degrees shy of being 360 degrees. In other words, it's 360 degrees minus 14 degrees, or 346 degrees. Another easy way to name this angle is to use the 14 degrees, but going in the clockwise direction means I have to use a negative value to indicate. So be careful. The reference angle is always up or down from the x-axis, never from the y-axis. So we're always adding or subtracting from 180 degrees or 360 degrees, or 0. Never from the 90 degrees positive y-axis or 270 degrees negative